Every rock sample ever collected from the moon, every single one across 6 decades of space exploration, came from the same side. The side facing us, the side we can see, the side that every ancient civilization painted faces onto, drew animals into, wrote myths about. And for 50 years, scientists built their entire understanding of how the moon formed, how it cooled, why it looks the way it does. All of it from material collected on one face of a two-faced world. Then China went to the other side, and what they found in that handful of dust is forcing scientists to rewrite the history of not just the moon, but of every planet, every impact, every catastrophe that has ever shaped a world in this solar system. Let us start with something that sounds simple, but is actually one of the strangest things in our sky. The moon always shows us the same face, always. It rotates at exactly the right speed to match its orbit around Earth, so one side permanently faces us, and one side permanently faces away. In all of human history, no person standing on the surface of Earth has ever seen the far side of the moon with their own eyes. You have to send a spacecraft around the back to even photograph it. And when we finally did, what we saw was completely unexpected. The near side, the one we all know, is covered with dark patches. Broad, smooth, gray-black plains that spread across the surface like ink spilled on pale stone. These are called maria, from the Latin word for seas, because early astronomers looking through telescopes thought they might actually be oceans. They are not oceans. They are frozen lava. Ancient volcanic eruptions that flooded across the surface billions of years ago, filled in entire basins, and hardened into the flat, dark plains we see today. That is why the moon has that familiar pattern. The man in the moon, the rabbit, the toad, whatever your culture decided to see in those dark shapes. You are looking at an ancient volcanic landscape. Now turn the moon around. Go to the far side. And those dark plains are almost completely gone. The far side is pale. It is cratered. It is ancient looking in a completely different way. A landscape of hills and impact scars with almost no volcanic flooding at all. The crust on the far side is thicker. The chemistry is different. The volcanic history is different. One hemisphere of the moon had billions of years of eruption and lava flows. The other one barely had any. Scientists call this the lunar dichotomy, and for decades, nobody could explain why two sides of the same world could be so dramatically, fundamentally different. There were theories. Maybe the great ocean of magma that covered the young moon billions of years ago cooled unevenly, faster on one side than the other. Maybe tidal forces from Earth warmed one hemisphere differently. Maybe one giant ancient impact rewrote everything that came after. All reasonable ideas. But to settle an argument about rock, you need rock. And all the rock ever collected from the moon came from the same side. That is the whole reason Chang'e 6 existed. That is why China spent years designing a mission of extraordinary complexity. To go to the other side and grab some of what was there. And the location chosen was not random. It was chosen with the precision of people who understood exactly what they were looking for. On the far side of the moon in the southern hemisphere, there is a wound. It is called the South Pole Aitken Basin, and it is the largest confirmed impact basin in the entire solar system. Measuring roughly 2,500 kilometers across, it is the deepest structure on the moon, formed somewhere between 4.2 and 4.3 billion years ago. That is 450,000 years ago, in the earliest violent era of lunar history when the solar system was still being assembled by catastrophic collisions. Whatever hit the moon to make that basin did not scratch the surface. Gravity measurements show the crust beneath it is among the thinnest anywhere on the moon. Scientists estimated the impact excavated material from between 80 and 120 kilometers down, reaching through the lower crust and possibly into the mantle itself, the deep interior of the moon that nothing else has ever touched. Inside that enormous basin sits another one. The Apollo Basin, a structure about 490 kilometers wide. And inside that, on a flat plain of dark basalt lying between the inner ring and the southern rim, is where Chang'e 6 came down, roughly 41 degrees south, 154 degrees west. The basalt underfoot has been dated to somewhere between 2.79 and 287 billion years old. The scientific hope was specific. If the original impact really did punch down into the deep interior, then some of that deep material might still be lying in the basin. Scoop up the surface here, and you might accidentally be scooping up the inside of the moon. Chang'e 6 launched on May 3, 2024, on a Long March 5 rocket from Hainan Island. The whole spacecraft stack weighed about 8,200 kilograms. The lander alone weighed 3,200. 5 days after launch, it entered orbit around the moon. But here is where the first remarkable technical challenge came in. You cannot talk to a spacecraft on the far side of the moon. Radio signals do not bend around 3,500 kilometers of rock. Every command, every piece of telemetry, every byte of data has to go somewhere else first. That somewhere else was Queqiao 2, a relay satellite already positioned where it could see both the far side and Earth simultaneously. Without that satellite, Chang'e 6 would have been completely deaf and mute the moment it crossed the horizon. On May 30th, the lander separated from the orbiter. 2 days later, the descent began. The spacecraft came down autonomously, using a visible light camera and a laser three-dimensional scanner reading the ground beneath in real time, picking out boulders and slopes, steering around them without any human in the loop. There was no time for a human to intervene. There was no signal path for a human to intervene through. 17 minutes after the descent started, it was on the surface of the far side of the moon. Then the collecting began. A robotic scoop for the surface material, a drill for what lay beneath, reaching about 2 meters down. The scooping was done in 8 separate passes at a single location, each one going no deeper than 3 centimeters, collecting around 1,010 grams of surface material on its own. There was even a small 5-kilogram rover riding on the lander, nicknamed Golden Toad for its gold insulating sheeting, which carried an infrared spectrometer for studying surface composition and looking for water ice. After sampling finished, the little rover detached, drove to a suitable spot, and photographed the lander sitting on the far side of the moon. It did all of that entirely on its own. On June 3rd, the ascent vehicle lifted off from the top of the lander. First time anything had ever lifted off from the far side of the moon carrying cargo. It found the orbiter in lunar orbit and docked with it automatically with no human flying either vehicle. The sample container was transferred into the return capsule. On June 25th, a re-entry module hit the top of Earth's atmosphere, skipped off at once to shed speed like a stone skipping on water, and then descended on a parachute to land in Inner Mongolia. 53 days from launch to landing. A total of 1,935.3 grams of material from the far side of the moon, the first samples ever collected from that hemisphere in the entire history of our species. 3 days after landing, in Beijing, the sealed container was formally handed from the head of the Space Administration to the Vice President of the Chinese Academy of Sciences. Certificates were exchanged, and then the mission spokesperson said something easy to overlook. He said the samples were more viscous than previous samples, that there were clumps. He was careful. He called these observable characteristics, not conclusions. A man describing what he could see and declining to say what it meant. He was describing the first discovery. It just did not look like one yet. The first measurement anyone took was density. And it came back wrong. Lunar soil from the near side sits in a well-understood range. Chang'e 5 soil from the near side had a bulk density of about 1.24 grams per cubic centimeter. Apollo samples range from about 0.75 up to 2.29. The Chang'e 6 soil measured 0.983 grams per cubic centimeter, barely denser than water. The first material ever collected from the far side of the moon was fluffier, measurably, consistently fluffier than any lunar soil ever handled before. The answer came from the ingredients. Lower density means lighter components. And when researchers ran the mineral analysis, what they found did not look like the near side at all. The soil was about 32% plagioclase, a pale, low-density feldspar, nearly 20% augite, around 10% pigeonite, roughly 3.5% orthopyroxene, just under 30% amorphous glass. And olivine, a dense, heavy mineral common in near-side samples, came in at just half of 1%. For comparison, Chang'e 5 near-side soil ran about 4.3% olivine. The far-side sample had roughly a tenth of the olivine and considerably more glass. But the detail that mattered most was the orthopyroxene. That mineral is not typical of the local basalt at the landing site. Its presence means something arrived there from somewhere else. Based on the proportion of orthopyroxene within the total mineral content, researchers estimated that at least 11% of the sample is foreign material. Debris flung in from other impacts elsewhere on the moon. Factor in the excess plagioclase, and that fraction could be higher. Analysis of bright ejected material crossing the dark plane around the landing site independently suggested contamination of at least 13%, which means the container held a mixture. Local ground plus wreckage thrown in from other impacts, some of them potentially reaching very deep indeed. The grains themselves are almost unimaginably fine. Researchers measured more than 72 million individual particles smaller than 1 millimeter. 95% fell between roughly 1 and 11 micrometers across, averaging about 5.5 micrometers. In geological terms, that is clay to fine silt, the product of billions of years of micrometeorite bombardment slowly grinding solid rock into powder in a vacuum. Among that dust sat larger fragments. Basalt made up 30 to 40% of them. Breccia, broken rock welded back together by impacts, another 30 to 40%. Agglutinates, grains of soil fused by impact glass, 20 to 30%. And about 10% were pale fragments dominated by anorthosite and norite. There were glass beads too, Small, rounded, colored black, brownish yellow, white, and green. Chemically, the local basalt was low in titanium, low in aluminium, and low in potassium. The soil showed very little uranium and thorium, far below the levels found in the chemically enriched terrain that dominates the near side. Whatever this place was, it had not been built from the same enriched material that produced the great dark seas we can see from Earth. Now here is where the story goes from interesting to genuinely shocking. Because ground truth, knowing what the far side is made of, was only the beginning. The bigger question was what had happened to it. And to answer that, researchers at the Institute of Geology and Geophysics of the Chinese Academy of Sciences, led by Professor Tian Hengqi, focused their attention on a single element, potassium. Potassium is what geochemists call a moderately volatile element. It does not need to be blasted apart to leave a rock. It only needs to get hot enough, and then it simply evaporates. And when it evaporates, it does not leave evenly. Potassium comes in two forms. Potassium-39 is lighter. Potassium-41 is heavier. When molten rock boils away into a vacuum, the lighter form escapes more readily than the heavier one. What remains becomes progressively enriched in the heavy version, which means the ratio of potassium isotopes in a rock is a thermometer, not of today, but of the worst day that rock ever had. Measure that ratio precisely enough, and you are reading a record of temperature and pressure left behind by an event that happened billions of years before there was anything alive to witness it. The team hit a wall immediately. The Chang'e 6 samples were mostly dust. Finding individual grains large enough to work with for precision isotope measurement was extremely difficult. Traditional methods demanded far more material than they had. So rather than requesting more sample, they rebuilt the method. They developed an ultra-low consumption potassium isotope protocol capable of high precision measurement at the milligram level. In the end, they worked with 4 basalt fragments. The heaviest weighed about 19 milligrams, the lightest about 14. 4 small stones sorted out of the soil under a binocular microscope in a clean laboratory, washed in ethanol, scanned by X-ray tomography to confirm what they were without cutting them open, then dissolved, purified, and fed into a mass spectrometer. The result published in the Proceedings of the National Academy of Sciences in January 2026 did not match anything from the near side. The Chang'e 6 basalts were isotopically heavier in potassium than every previously documented lunar basalt, heavier than Apollo, heavier than Chang'e 5, heavier than the lunar meteorites. The offset averaged about 0.16 parts per thousand above the Apollo baseline. The iron isotopes came out heavier too. Now in isotope geochemistry, differences that small are not casually interpreted. They are attacked. The team went hunting for every boring explanation they could find. Could it be cosmic rays? Over hundreds of millions of years, radiation can alter isotope ratios through nuclear reactions. The team calculated the maximum possible contribution even at an exposure age of 1 billion years, an upper limit for most lunar samples. The effect fell inside their own margin of error. Not enough. Could it be contamination from surrounding soil? Fine lunar dust does acquire heavy isotope signatures from space weathering, but the fragments had been ultrasonically cleaned, and the tomography scans showed no issues. Could it be ordinary magma chemistry? This answer split in two. Modeling showed that melting and crystallization processes could largely account for the heavy iron signature, but potassium behaved differently. Because of how potassium moves during melting and crystallization, those processes leave its isotope ratio essentially untouched. The magma could not have done it. Could it be the original impactor mixed into the mantle? The team ran the numbers for chondrites, iron meteorites, and Vesta-like bodies. Chondrites would have driven the isotopes lighter, not heavier. Iron meteorites contain almost no potassium at all, and a Vesta-like impactor would have required at least 7% of its residue to survive in the lunar mantle while pushing the iron isotopes in the wrong direction. One by one, the ordinary answers failed, which left the extraordinary one. Here is what the data suggests. The mantle beneath the South Pole Aitken Basin does not merely contain heavy potassium today. It was already heavy before these basalts ever formed. The signature was not created on the way up from the mantle to the surface. It was inherited from below. Something reached into the deep interior of the moon and cooked it. Numerical simulations of the South Pole Aitken impact suggest it could have raised mantle temperatures to around 2,800 Kelvin, comfortably hot enough to vaporize potassium. And the moon has no atmosphere to hold vapor in place. Anything that boils, leaves. The remarkable part is how little needed to escape. Under vacuum conditions, isotope separation is brutally efficient. Modeled as simple distillation, a loss of just 2% of the potassium in that deep region fully accounts for the signature measured in those 4 fragments. For iron, less than 2%, just 2% evaporated. That is all it took to leave a fingerprint still legible 4.25 billion years later. Separate work published in 2025 in a Chinese Academy of Sciences journal went even further. By dating zirconium-bearing minerals inside certain rocky fragments in the Chang'e 6 samples, researchers pinned the age of the South Pole Aitken impact itself at 425 billion years ago, a date that had been debated and estimated for decades but never confirmed by direct physical evidence. Now it was confirmed. The largest impact basin in the solar system was dated by the rocks it left behind. This finding carries a consequence that reaches far beyond one crater on one moon. Volatile elements are part of what makes magma eruptible. They lower melting points. They help molten rock rise, strip them out of a region of mantle, evaporate them away in the heat of a catastrophic impact, and that region becomes harder to melt and less willing to erupt. Which means the impact that dug the largest hole on the moon may also have quietly turned down the volcanism of an entire hemisphere. The dark seas, the patches we have watched our whole lives, that every culture on Earth has drawn a face or an animal into, their absence on the far side may not be a coincidence of geography. It may be the scar tissue of a single morning 4.225 billion years ago when something enormous hit the moon and boiled its interior. The data also revealed that the mantle beneath this hemisphere holds less water than the mantle beneath the near side. Less water, less potassium, less of everything that helps rock melt and erupt. One impact created a chemical desert deep inside the moon, and the volcanic silence of the far side, the pale, cratered, lava-free face that is so different from what we see, is the surface expression of that ancient chemical stripping happening thousands of kilometers underground. Researchers have already built a catalog of 1,674 major source craters capable of having thrown debris onto the Chang'e 6 landing site, some of them drawing material from as deep as 3 kilometers underground. Together, those impacts appear to have delivered a layer roughly half a meter thick across the sampling region. Their estimate is that the returned material is about 93% local basalt, about 6% material from the South Pole Aitken Basin itself, the fraction most likely to contain genuine mantle components, and roughly 0.5% highland material from entirely outside the basin. 6%. That is the piece everyone is really after. Somewhere in that 1,135 grams of dust and glass beads and welded fragments sitting in laboratories in Beijing, there may be grains of the actual inside of the moon, material that started its journey to the surface not as a volcanic eruption, but as wreckage thrown up by the most violent collision in lunar history. The rest of the work is still ahead. Scientists have access to almost 2 kilograms of far-side material, and most of it has not been touched yet. Applications to study the samples have opened to Chinese institutions, and the Chinese Space Administration has said it welcomes proposals from scientists in other countries. More missions are coming to this region. Several agencies have their sights on the South Pole Aitken Basin, drawn by permanently shadowed craters near the lunar South Pole and the water ice believed to be locked inside them. But step back from all of this for a moment. For the entire history of our species, every myth, every observation, every telescope pointed at the sky, every one of the 11 sample return missions before this one, all of it was directed at a single hemisphere of a world that turned out to have 2 completely different halves. We assumed we understood the moon. What we understood was the side that faces us. And when we finally reached around and took a handful from the other side, what came back was soil too light to be familiar, glass where there should have been stone, olivine that had nearly vanished, and 4 small fragments carrying the chemical memory of a day when the deep interior of the moon grew hot enough to boil. Those 4 fragments weigh less than a paperclip, but the information inside them is billions of years old and changes everything. The dark seas we know so well, the ones that make the face we all grew up seeing in the full moon, they are not a feature of the moon. They are a feature of the side that got to keep what it started with, the side that survived. The other side lost something essential in a single catastrophic moment more than 4 billion years ago. Lost it to heat, to vaporization, to the violence of the largest impact in lunar history. And because it lost it, it could never build the same volcanic landscape. It went quiet. It stayed pale. It stayed different. 4 small fragments, less than 80 milligrams of rock between them, and inside them, the proof that a single impact can reach into the deep interior of a world and permanently change its chemistry, permanently alter its volcanic future, permanently write the story of what one hemisphere will look like for the rest of time. If that can happen to the moon, it can happen elsewhere. It tells us something new about how planets are shaped, not just by slow geological processes over billions of years, but by single catastrophic mornings that rearrange the interior of worlds in ways that last forever. China went to the side of the moon that nobody had ever touched. And what they found there rewrote 4 billion years of lunar history in 80 milligrams of ancient dust,